This is the beginning of Chapter 9. In Chapter 8, which was about hypothesis testing, we were looking at characteristics from a population. In Chapter 9, this is about inferences from two samples. In other words, we'll be comparing characteristics from two populations. The goal is to compare two sets of data representing two populations in order to test claims about how the two populations compare to each other. And so here are some examples. For example, we compare means or averages. Compare the average daily internet time for male college students versus female college students. Or compare the mean weight loss of one diet program versus another diet program. So this is about means and averages. Or compare average scores on a standardized test before and after students before a study program. And of course, we can also compare other population characteristics like proportions or percentages. Pardon me. So we can compare, for example, the percentage of female smokers with the percentage of male smokers. We can compare the proportion of households with internet access within major cities versus households in rural areas that are outside major cities, etc. So we are looking at samples, and the big question is, when there is a difference in the samples, is the sample difference significant enough to say there's a difference in the two populations? In other words, can we infer from a sample differences something about the differences in the populations? So let's say it again. The big question is, when there's a difference in the samples, is the sample difference significant enough to say there's a difference in the two populations? In other words, can we infer enough from the samples to make a prediction about the populations? Here's a brief algebra review that we need later on. When x1 minus x2 is equal to 0, then x1 equals x2. x1 equals x2. When the difference between x1 and x2 is positive, then x1 is greater than x2. And when x1 minus x2 is negative, then x1 is less than x2. The first thing we'll be doing is testing the difference between proportions. And so we're using the same 6-step hypothesis test that we had before. So we state the null and alternative hypothesis, H sub naught, or H naught and H1. And of course, the alternative hypothesis has a not equal, greater than, or less than. And then if it's not equal to 0, we have a two-tailed test. And then we have a right-tailed test as before, and a left-tailed test in this particular case, if P1 is less than P2. Now, it's important to designate which population we are labeling as population 1 and which is population 2, because this will affect the direction of the comparison, which determines whether the test is right-tailed or left-tailed. Okay? So we need to be careful about that we are consistent about that. And as before, step 3 is we graph the distribution and the rejection region using critical values for alpha in the direction of the test, like left-tailed or right-tailed. And is it a z-critical or a t-critical value? Right-tailed, left-tailed, or two-tailed? So these are the basic questions that will come up as we do the examples. And step 3 would be to compute the test statistic. If it's a z-score or a t-score, so if it's a hypothesis about the mean, we use a t score. And so here it's the population, difference population means divided by the standard deviation for the test. And we specify that in a little bit. Similarly, when we have the hypothesis about the population proportion, we use a z-test statistic, and that's p hat 1 minus p hat 2 divided by the standard deviation for the test. Again, we'll specify what that is. It's a little bit more complicated, but you'll see how that all works. Then step 4 is we compute the p-value. We're assuming that the null hypothesis is true. How rare is the z-score, or the t-score? And again, we can easily compute the p-value when we have a z-score, but if we use the t-score, that gets difficult, and we typically want to use technology to come up with an accurate answer. We get a range perhaps when we do the t-score, but to get the real p-value, we need to use technology. Step 5 is about making a decision to reject the null hypothesis or not reject the null hypothesis, or fail to reject the null hypothesis. So we reject if the classical test computed test statistic is in the rejection region, or we look compare the p-value with alpha for the test. Otherwise, we cannot reject the null hypothesis. Again, this is exactly what we have done before in the previous chapter, in chapter 8. And then number 6 would be to state the conclusion with this particular level of significance. This data does or does not provide significant evidence to conclude that, and then whatever was written in the alternative hypothesis. Again, this is exactly what we have done before in chapter 8. Let's talk for a moment about the notation for two proportions. So P sub 1 is the population proportion for the first population, N1 is the sample size for the first population, X1 is the number of successes in the sample, and then P1 hat is X1 divided by N sub 1. That's called the sample proportion, and the same notation holds true for the for population number 2, where we have subscripts instead of 1, we have subscripts with the number 2. And then, of course, Q1 hat is equal to 1 minus P1 hat. Now, here's a new term. It's called pooled sample proportion. P bar is equal to X1 plus X2 divided by N1 plus N2. And then Q bar would be 1 minus P bar. So this is the notation that we'll need here for the upcoming examples. So the formula for the test statistic when testing the difference between two population proportions is Z equal to P1 hat minus P2 hat divided by the standard deviation for the test. Standard deviation for the test. Now, the standard deviation is equal to, so S, sample standard deviation, is equal to an expression which is a little bit complicated. So the standard deviation is equal to the square root of P bar times Q bar times 1 divided by N sub 1 plus 1 divided by N sub 2, and where we had defined P bar as the pooled pooled proportion on the previous page. So P bar is equal to x1 plus x2 divided by n1 plus n2. n1 plus n2. Let's look at an example. A survey of 1,500 adults in California and 1,000 adults in Oregon found that the percentage who were smokers in each state to be 18.4% and 20.7% respectively. At alpha equals 0.05, does this data indicate that the proportion of adult smokers is lower in California than in Oregon? So let's write down the information that we have. We are dealing with many different variables, so it's important that we are very specific and deliberate about how we label things. So here P1 is a proportion of Californians who are smokers, and P2 is a proportion of Oregonians who are smokers. And now we're setting up the data for California and Oregon. So we write our null hypothesis and our alternative hypothesis. P sub 1 equals P sub 2, and for the alternative hypothesis, P sub 1 is less than P sub 2, so we have a left tail distribution with alpha being 0.05, so that's the area here. That means our critical value, Z sub 0.05, is minus 1.645. So that's our critical value. Before we can compute our test statistic, we need to evaluate our pooled sample proportion P bar, and it was equal to x1 plus x2, so that's 276 plus 207 divided by n sub 1 plus n sub 2, so it's 1,500, 1,500 plus 1,000, and that ratio is equal to 0.1932, and that means that Q bar is equal to 1 minus P bar, so Q bar is then equal to 0.8068. So now our formula for the Z statistic was P1 hat minus P2 hat. So we have 0.184 minus 0.207, all divided by the standard deviation. And according to the formula we had before, it's equal to P bar times Q bar. So it's 0.1932 times Q bar times 0.8068 times 1 divided by n1, which would be 1 divided by 1,500, plus 1 divided by 1,000. And the corresponding p-value, is equal to 0.0768. There's our p-value. So now when we look at the test statistic, it's certainly not in the rejection region. So based on that, we failed to reject the null hypothesis. Failed to reject the null hypothesis. Similarly, when we look at the p-value, the p-value is not less than our alpha. That's a no. Again, that leads us to conclude to fail to reject the null hypothesis. Fail to reject the null hypothesis. And since we're dealing with a z-score here, we simply looked up the p-value by looking at the critical value of minus 1.645. And we found the corresponding area under the curve is 0.07. Well, this is interpolated 6.8. So, but it's close enough for the p-value. And again, that tells us that we failed to reject the null hypothesis. In summary, we can say that at the 5% level of significance, this data does not provide significant evidence that the proportion of smokers in California is less than in Oregon. Before we get into the discussion of on the confidence level for the interval, for the difference, we need to talk about the confidence level based hypothesis test alpha. If the hypothesis test was one-tailed, balance with a matching area in the opposite tail. So here's what this looks like. So let's say we have a left-tailed hypothesis test. So here's our alpha. Let's just say it's 0.05. What it means is we have to balance it with the 0.05 level on the other side, on the opposite tail. That means in the middle we have 90%. So in other words, we use a confidence level based on the area remaining between the two balanced tails. So if this was 5%, we balance it with 5% on the other side, and that gives us 90% in the middle. So in this example, we use a 90% confidence interval. To estimate the difference between the proportions. So again, for this example, we use a 90% confidence interval to estimate the difference between the proportions. So this is then our confidence interval, P1 hat minus P2 hat minus the margin of error, less than P1 minus P2, the population proportions, and less than P1 hat minus P2 hat plus the margin of error. And where the margin of error is computed as z sub alpha divided by 2 times the square root of P1 hat Q1 hat divided by N1 plus P2 hat times Q2 hat divided by N2. So obviously there are a lot of calculations, and if you can use technology, that would be very, very helpful in terms of saving time and getting the accuracy that you want. In our case, it turns out that the margin of error would be equal to 1.645, and this expression is equal to 0.01626. So that's equal to 0.0267. And so then using our P1 hat and P2 hat, our confidence interval then turns out to be from minus minus 0.0497 to 0.0037. Now notice that the confidence interval contains 0, which is an indication that it contains, that we failed to reject the null hypothesis. So the observation is that when the bounds of the confidence interval include 0, the computed difference between P1 and P2 is less than the margin of error. So now a particular example, we can say because 0 is in the interval, in the confidence interval, there's no significant difference between the two proportions. Let's look at confidence intervals and what the endpoints mean. If P1, if the positive if both endpoints are positive, P1 and P2, then P1 must be greater than P2, must be greater than P2 between the lower and upper bounds. When we have P1 minus P1, P2, and they're both negative endpoints, so negative endpoint, then that means that P1 must be less than P2. And if P1 is negative and the other endpoint is positive, now we know that the interval includes 0. Again, then there's no significant difference between the two proportions. Like we had in the previous example. So let's look at an example which is more intuitive. Let's say P1 is a proportion of pet owners who identify themselves as dog people, and P2 is a proportion of pet owners who identify themselves as cat people. And let's say the P1, P2 confidence interval is 0.06 to 0.11. So that means that the proportion of pet owners who are dog people is greater than the proportion of cat people between 6% and 11%. 6% and 11%. Obviously that's 6% and this is 11%. Let's say the P1, P2 confidence interval is minus 0.08 to minus 0.02. That means the proportion of pet owners who call themselves dog people is less than the proportion of cat people between 2% and 8%. And example number 3, if the P1, P2 confidence interval is minus 0.03 to positive 0.05, we notice that this interval includes 0. And so we can say there's no significant difference between the proportion of pet owners who say they are dog people and the proportion who say they are cat people. So again, in the third case, where the confidence interval includes 0, we can say there's no significant difference between the proportion of pet owners who say they are dog people and the proportion of people who say they are cat people. I use quotation marks. Let's look at another simple example. An economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. He obtains a random sample of 800 urban households and finds that 338 of them have internet access, and he obtains a random sample of 750 rural households and finds that 292 of them have internet access. Test the economist's claim at the 5% level, alpha of significance. So here's our information summarized. P1 is a percentage of urban households with internet access, and P2 is the percentage of rural households with internet access. And then for the urban internet, we have X1 as 338, and N1 was 800, so that gives us a P1 hat. The ratio of these two numbers is 0.4225. And for the rural internet, our X2 is 292, and N2 is 750. That gives us a P2 hat of 0.3893. So we write our null and alternative hypothesis. P1 equals P2 is our null hypothesis. And the alternative hypothesis is that P1 is greater than P2. And here's our distribution. It's a right-tailed test because P1 is greater than P2. And this area is 0.05. That means our Z critical value is 1.645. 1.645. Using technology, we find out that our Z statistic is 1.320, so which is about here. So it's certainly not in the rejection region. So we failed to reject the null hypothesis. Similarly, the p-value is 0.092. That means it is greater than alpha. Again, that leads us to conclude that we failed to reject the null hypothesis. So that is our decision here. We failed to reject the null hypothesis. When we compute the confidence interval, and remember it needs to be 90% because we need to balance the right side with the left side, the 5% as explained before. So in the middle we have 90%. So for the 90% confidence interval, our confidence interval is minus 0.0079 and to 0.07419. And because the confidence interval contains 0, we conclude there's no significant difference between the two population proportions. So the confidence interval, the 90% confidence interval contains 0, so that means there's no significant difference between the two population proportions. Again, that leads to rejection of, we fail to reject the null hypothesis. Here's another example. A random sample of 153 people ages 16 to 19 was taken from the island of Oahu, Hawaii, and 12 were found to be high school dropouts. Another sample of 256 people, same age range, was taken from Sweetwater County, Wyoming, and 14 found to be high school dropouts. Does this data indicate that the population proportion of high school dropouts on Oahu is different either way from that of Sweetwater County and Wyoming? Use alpha 10% or 0.1. So P1 would be the dropout percentage in Hawaii, and P2 would be the dropout percentage in Sweetwater County, Wyoming. So then for Hawaii, our X1 is 12, and our N1 is 153, and for Sweetwater County, Wyoming, X2 is 14, and N2 is 156. Writing our null and alternative hypothesis, our null hypothesis is P1 equals P2. And the alternative hypothesis, notice the wording, the question here Does this data indicate that the population proportion of high school dropouts on the WOW is different either way? So that means P1 is not equal to P2. So we have a two-tailed distribution. So we have our distribution here, and since alpha is 0.10 or 10%, each area has 0.05. That means our critical value, Z critical value is minus 1.645 and plus 1.645. And these, of course, are the rejection regions. Using technology, our Z-test statistic is 0.952, and our p-value, again using technology, is 0.341. So in other words, our critical values are minus 1.645 and 1.645, and our test statistic is 0.9. So we are not in the rejection region. So we failed to reject the null hypothesis. And since this is our p-value, that is greater than our alpha value 0.10, so we fail to reject the null hypothesis. We fail to reject the null hypothesis on both counts. So our conclusion is that at the 10% significance level, there's not sufficient evidence to conclude that the proportion of dropouts is different in Hawaii compared to Wyoming. Using technology, we can say that at the 90% confidence level, the difference between the two population proportions is insignificant. It contains 0. Again, it supports what we said earlier, that we failed to reject the null hypothesis. So again, here we use technology to determine the confidence interval based on 90% confidence. And so we say since the interval contains 0, there's no significant difference between the dropout rates in Hawaii and Wyoming. The next example is about phone taps. A recent gender social survey asked the following two questions of a random sample of 1,483 adult Americans under the hypothetical scenario that the government suspected that a terrorist act was about to happen. Do you believe the authorities should have the right to tap people's telephone conversations? At the alpha equals 0.01 level, is there evidence to conclude a higher percent of men believe it is okay to tap phones under the hypothetical scenario of suspected terrorist activity than women do? And then the last question is, if so, how much more? Find the corresponding, figure out the confidence level for the difference. So first of all, we summarize our data. We say, okay, for the male who say yes, X1 is 472 and N1 is 796. So that gives us a P1 hat of 0.593. And for the female, yes, X2 equals 337, N2 equals 687. Then our P2 hat is 337 divided by 687, which is 0.4905. So we write our hypothesis. The null hypothesis is P1 equals P2. The alternative hypothesis is that P1 is greater than P2. We have a right tail distribution with 0.01 in the right tail. That gives us a critical value of Z equals 2.326. 2.326 is our critical value. And when we compute our test statistic, our test statistic is, let's see, what was it? 3.0 3.95. So Z, our test statistic, was 3.95 using technology. And then our p-value turned out to be less than 0.0001. So you look at the table, and so we agree that for that kind of a Z test statistic, our p-value is basically 0, but since it cannot equal 0, we make it less than 0.001. So therefore, our decision is very clear here. At 3.95, we are way into the rejection region. And since the p-value is less than alpha, p is less than alpha, so we reject the null hypothesis on both counts. Reject null hypothesis. Because we're in the rejection region and the p-value of 0.001 is less than 0.01. So our conclusion is then that at the 1% level of confidence, this data does provide significant evidence that a higher proportion of men believe it is okay to tap phones under the hypothetical scenario about the terrorists, see above, than women do. So that's our conclusion. Now let's take a look at the confidence interval. Now for the confidence interval, we need to remember that we're dealing with the right tail distribution, and the tail is 1%, so therefore we need to balance it with another 1% on the other side. So in other words, we're looking at a 98% confidence interval. 98% confidence interval. And using technology, that interval turns out to be 0.04235. At the lower end, and at the upper end, it is 0.16251. So what that says that between 4.2% and 16.3%, more men say it's okay for government phone taps than women do. So 4.2% to 16.3%. More men say it's okay for the government to tap the phones than women do. So that's what the confidence interval tells us. And remember, it's got to be 98% because we need to balance the 1% on one side with the 1% on the other side. So we have 98% in the middle for the confidence interval. This concludes section 9.2.